Hi, this is Leif Nilsson from Surge Copper, recording this video to accompany our April 12, 2022 press release, where we released the results from our 2021 ZTEM airborne geophysical survey across the Ootsa and Berg properties in central BC. So as a bit of background, what is ZTEM? Well, it's an airborne geophysical survey system. It's got a few sensors that are towed by a helicopter, as well as some sensors that remain fixed on the ground. All of these sensors are essentially measuring changes in the local magnetic field, which are caused by currents flowing in the subsurface. Those currents in turn are driven by atmospheric EM fields. Those atmospheric EM fields are a particularly special part about the system. So they're very long wavelength natural EM fields that originate very high in the upper atmosphere. Those provide several benefits to the system. So one is that there's no transmitter required, so you don't have to produce your own signal. These waves happen to propagate vertically into the earth, which simplifies a lot of the math involved. And because they're very long wavelength, they can penetrate several kilometers deep into the Earth's surface. So taken together, there's a few key advantages to the system. One, it's very cost effective. It can cover huge areas very quickly. Secondly, the use of natural fields allows you to effectively image the entire explorable volume of the survey area. And lastly, the design of the system leaves it relatively immune to rugged topography in the area. So all these things combined make it certainly one of the ideal systems for use in exploring porphyry copper districts like what we're doing. So just a bit on the data and images that come out of the system before I jump into some of the results from our survey. The ZTEM system produces what are called tipper data, which are in fact complex transfer functions which relate the vertical magnetic field component, which comes from the towed sensor, to the horizontal magnetic field components, which come from the fixed ground-based sensors in the survey. So because they're complex functions and you're relating different directional components, you end up getting multiple data sets. So the Z to the X, the Z to the Y, real, imaginary, and then different frequency bands therein. So it produces a lot of complexity when it comes to trying to interpret results. As a result, one of the key summary products, if you will, is something called the total divergence parameter, which basically takes a number of these data inputs, performs a derivative function on them, and combines a bunch of them into a single parameter that shows relative or local maxima and minima corresponding to resistivity, which is quite a bit more intuitive, to look at, as opposed to the normal crossover response that tipper data produces at a resistivity contrast. The images at right here are an example of what's called forward modeling. So if you have a theoretical subsurface conductor, so what's drawn here is basically a prism-shaped conductor with a hole in the middle that is a resistive core. So it's a very sort of cartoon version of the rough geometry of an ore deposit that would have a conductive outer ring and a resistive core. So using theoretical analytical arguments, you can calculate what the expected tipper response to such a subsurface conductor would look like, and express that in this total divergence parameter that I'm referring to. And the image at the bottom right shows what that looks like, and it'll become clear why I'm showing that in a moment. A big part of geophysics is, of course, the reverse of this problem, which is called inversion modeling. Inversion modeling, asks and answers the opposite question of what buried conductors or what buried resistivity distribution in the subsurface would give rise to the observed tipper data. So I'll start going through the results from our survey, and it's a combination of really raw DT data from the survey, as well as inversion modeling performed on that data to show subsurface resistivity distributions that give rise to that data. Just some of the specifics on our survey. So it was a 4,224 line kilometer survey covering about 1,154 square kilometers, 300 meter line spacing. Between the combined Ootsa and Berg properties, it covers 4 known porphyry copper deposits, as well as numerous known targets. In terms of the final products that we'll be going through here, Tipper data processing plus apparent resistivity inversion products using both 2D and 3D algorithms, all of which were provided by Geotech. So what's shown here is really a couple of the final results from the survey. So on the left is that total divergence map. So this is a plan map looking down on the district. You got the whole survey area covered here. And again, this is the single parameter that effectively combines all of the raw Tipper data and is shown in such a manner that local maxima and minima here roughly correspond to the resistivity that gives rise to that Tipper response. On the right is an inversion product. So this is now in units, physical units of ohm meters. So this is produced by the 3D inversion algorithm. And what we're showing here is really just a subset of that model showing in 3 dimensions an isosurface for 100 ohm meters. So what I would highlight on these summary images is that there's basically 3 main areas of the overall districts, at least in terms of our survey area, where we see a large number or preponderance of interesting anomalies that warrant a lot of follow-up. The first is going to be in this area to the southeast. So this would include the seal and ox deposits in the area extending eastward from there. The second area is up in the north of the district. So that would include the Berg Deposit, the Brightall Target, as well as really a number of new showings and targets, some of which have had a little bit of work done on them in the past. Others, such as this northeast target, really have had no historical exploration. So lots going on up in that portion of the district. And lastly, this area straddling the border between the Berg and Ootsa property. In some cases, or some of these targets are right along the border as well, with Imperial's ground just to the south of the Huckleberry mine. So now I'm going to start going through some of the deposit and target level data features. So I'll start first with Berg, mainly because it's probably the cleanest signature among the known deposits that we've seen in the survey. Geologically, that makes sense. The Berg deposit has considerably less faulting than some of the other deposits in this area. It's quite a clean and preserved deposit. There isn't significant fault offsetting or anything like that. The nature of the deposit, the mineralization is hosted in the wall rocks surrounding a central intrusion, and that just shows up very clearly in that plan-oriented DT image. So we've zoomed into that over there on the right. You can see the footprint of the Berg mineralized zone, really straight on top of that circular donut feature that you see in the DT image. So going back to that forward modeling example I gave at the start, this is why I was highlighting that. A lot of the deposits in this area have that characteristic shape of a central resistive core, and a lot of the mineralization hosted in a more conductive anomaly that forms an annulus or donut around that central core. And so you tend to see in the DT image this sort of circular feature. So these circular features will be prominent in the data, but perhaps the cleanest one, at least insofar as known deposits go, is certainly right here at Berg. Same thing, just in cross-section view. So over on the left, you have a cross-section from some recent drilling done at Berg. So you can see the central intrusion there with much weaker mineralization, and the vast majority of the grade is hosted in this the areas around that intrusion. So in this section, which is looking up to the northwest, it's over on the southwest and the northeast. And then similarly in a pseudo section in through the 3D resistivity model, you see that feature imaged extremely well. So this is again cut vertically through the ore deposit, or a pseudo section through the 3D resistivity model. with the drilling superimposed on that, so that that more resistive central intrusion is imaged very cleanly, right up to the contacts with the more conductive zones where most of the drilling and the grade is hosted. So very, very impressive visualization or imaging of the deposit at Berg. Mineralization at Berg is known to be open at depth. It's a pit constrained resource, but there's been a few deep holes that have shown that it continues at depth. So it's certainly heartening to see that that large conductivity anomaly at depth, which would suggest that the deposit certainly has quite deep roots to it. Moving on to the Seal deposit. So again, a simplified geology map over on the left. Seal has quite a bit more sort of complicated structural features to it. It's been moved around a bit by some post-mineral faults, but it shares some of the same features as a lot of other deposits in this area, with a central weakly mineralized intrusion and a lot of the mineralization sort of flanking that in the host rocks, the wall rocks rather, around it. That orientation is reflected in the DT image over at right. Requires a bit more subtle interpretation, but you can sort of see a subcircular feature that's been moved around a bit, but it does correlate well with the areas of known mineralization at Seal. Similarly, in cross section or pseudo section through the 3D resistivity model, large conductive anomaly at Seal that correlates very well with the existing drilling. So again, another very clear image of the known deposit there. Moving on to Ox. So Ox is another example of a fault offset deposit. So simplified geology map on the left. The mineralization at Ox forms a half ring flanking a central intrusion, and it's been sort of cut off on the east side. Again, that shows up quite clearly in the DT image shown at right, where you see a half circular feature in the DT. And similarly, in the inverted resistivity image, the drilling and mineralization is again associated with a single conductivity anomaly here at Ox. Moving on to one of our main exploration targets in the district. So this is the burgett target located just due east of Berg. What's shown on the left is the compilation map with a number of different data sets, including surface total magnetic intensity and copper in soils. So this target is quite a bit more structurally complex. There's another fault that runs through here. And when you look at this target in the DT image, it's again a bit of a subcircular feature, but it's clearly been moved around a bit. So there's going to be some more subtle interpretation required here, but certainly the ZTEM data from this area is going to be or prove very useful in targeting and further exploration of this this known area of mineralization. And then again, in the 3D resistivity model, the known drilling or the historical drilling that's taken place at burgett, all of which is shallow but is tended to hit copper porphyry style mineralization. It is associated with a local conductor anomaly, and that anomaly itself has some pretty good depth extension to it, extending over 1,000 meters in places. So I want to highlight one of the regional targets that really sticks out like a sore thumb in the DT image, which for the time being, we're just referring to as the northeast target. So again, going back to that theoretical forward modeling example of why these things tend to look like circular features. This one is quite large, very clear. Certainly leaves us hoping that it's going to prove to be an intrusive center. There's also some very I think significant prospects in this wider area that have had very little exploration done historically. So that includes both the Cibola prospect as well as Sylvia, where there's been pretty large mapped alteration zones, as well as some historical drilling, including 63 meters grading 0.33% copper and 0.02% moly at Sylvia itself. So all these are in the general district of what looks like a potentially large intrusive center that's being imaged in this this DT map at right. That same target area is shown in a pseudo section looking to the west over there on the left. Again, showing a very similar type feature to what we saw at Berg, with a central resistive core and two very large conductor anomalies flanking that in cross section. So in summary, again, just focusing on some of these bigger portions of the survey area. So I'm showing here the northern portion on the left, and then the southeast portion on the right. Recognizing the fact that, looking through our known deposits, there's very clear footprints and patterns. There's a very clear importance for circular or modified circular features. That's grounded both in theory, but also in the known signatures of, or the signatures of the known deposits that we've gone through. The data also shows, very large scale structural patterns that, help us with mapping and correlating geology in this area. And really just a large number of targets across the entire district that are going to need to be followed up on. I'm showing on these maps just a number of circles around some of these circular features, many of which have really had, little to no work done on them in the past. So it's going to prove to be a very busy year as we start to prioritize and ground truth a number of these, exciting areas across the district. That's it. Thanks for watching.